Yes, thank you, Steve. So this presentation will go to the monitoring and control of both the power and BBU systems. My name is Hamid Kayhani, and I'm glad to present these slides together with Zoe Ibrahimzadeh and Patrick Williams, all from Facebook. Going through the main, just an overview of the main features of OpenRack v3 power and battery system. On OpenRack v2, we had a power and battery system as a fixed one module together. On v3, it's located. You can locate it anywhere in the rack. The power shelf and BBU on v2 were integrated. As I said, now they are separate and they are flexible in design. We have a flexible AC and EC DC input connectors. We have one power zone compared to the previous one. We are upgrading the voltage from 12 volt to 48 volt. And the most important topic for this presentation is the monitoring, that we are adding flexible monitoring features that allows different people around the world to use their own monitoring system to the OpenRack v3. And let me go by that. So this shows the power shelf mechanical design. As you can see, this has 6 PSUs, and you can see the AC and AC input and output connector. The important module that you can see on the left is a power monitoring module. This is the module that actually it has 4 connectors on the front. More details here. 4 connectors on the front. It can support it is unpluggable. So on the rear, you have all these different signals, and on the front, you have 4 RJ45s. The design has not been to be just supporting one kind of communication. We are actually, as of the OCP collaboration, we have 2 versions of this communication module. We call it PMC and PMI to support Modbus and Ethernet. We encourage anyone in the industry, if they want to use a different type of communication, to revise the electronics inside this module to have their own communication. I understand at this time the industry is not unified what the communication could be for the power system. There are the companies doing CAN bus, companies doing RS-485 or Modbus. Some companies I know that they do really the PM bus or I2C, they bring it up directly. There might be some other companies that use a lot of GPIOs. So this design actually supports all of them, all possible scenarios. It's a modular design. It can support all different type of the design. You can just, if you are good with this PMC or PMI that we are introducing, you are good to go. Otherwise, you just redesign the electronics inside this module, and you are able to communicate with our power shelf. And hopefully, if you design something differently, you can contribute it to OCP as well. We have a standard dimension for the power for this communication module. You can see the width and height and length here. On the front, there are 4 2x2 RJ45s. So you can connect, it can be used for Ethernet, CAN bus, GPIOs, and several other things. Even we recently tried to add a USB-C on the front. We will update the spec later. So if you want to do for debugging purpose, you can actually plug into that module as well for debugging purpose. Here it shows how the rear of this module looks like. It doesn't show the electronics. It's more of the spec requirements and how it plugs into at the shelf at the rear. Here it shows the cable. I think there are another version And some vendors actually designing with the with actually a PCB. So on the rear, there's a PCB that this module plugs into. Our spec doesn't require wire or PCB, so it's up to the vendors to decide. It just has to work with this module. So the dimension of the mechanical and the signals, the pinout and the signals and this rear Modbus are designed and fixed. It is a 2C at the rear. It's a 2C connector. It has, I guess, 84 pins, and we added a lot of several different type of signals at the on this at the edge connector on the rear, including the Modbus, I2C. There's a bunch of reserve signals for GPIOs, CAN bus. Even if you want to have your own A2D ADC, you can have it, and like all other things. And it's also been designed in such a way that it can work with the 48 volt. So the 48 volt directly come to this PCB, and with enough clearance requirements that you can have your own power supply inside this module to convert the 48 volt to 3.3 or whatever other voltage that you want. So this is like the base of the design, and that we came up with. And this, I mean, thank you to all of you that actually came up with brought us the comments and proposal that you want to have a design that works with your own top of the rack switch or your own approach. So that's the way that actually we try to have it, make it versatile to work for everybody in the industry. Moving forward, we have right now work on two approach of the communication. We call it PMC and PMI. The monitoring, the power, the shelf is a universal. You can use it for both of them are universal, so you can use it for both battery and power shelves. The communication, as I said, for the PMI is through Modbus, for Ethernet, for the Ethernet, for the PMC is through Ethernet, and there are GPIO signals if you want to use. There is a single bus downstream for monitoring and control of the BBU and PSU for remote firmware updates or your send to command. The mechanical and thermal design are also in deep are done in depth to make the requirement, especially the thermal. We're not going to update on the thermal today, but there is a team actually working on the thermal design to meet the requirements with passive cooling. Here shows, as a high-level block diagram. We have a power shelf and a battery shelf. You can plug in the PMC or PMI into the shelf, and from the shelf, and from there, you can plug it to the top of the rack. In this picture shows each one directly connect to the Tor. You can actually daisy chain them if you prefer, because there are 4 RJ45s on the front. So depends on your type of communication module. Hopefully you should be able to daisy chain if you want. Downstream communication, there's a downstream communication shows here as the internal buses. That one, we have not fully decided which bus to use. We are currently debating between Modbus and PM bus. We hopefully by the end of the year, we finalize that on which one to use. The Modbus is more versatile. It allows you, if your Tor is actually, you want to have a Tor to work at the Modbus, you can actually have a empty PCB for the Modbus application. It's hard for me to believe you want to have a PM bus directly going to the top of the rack, because there's like some sort of cable, and in this noise and signaling could be challenging, signal integrity. So there is a pros and cons between here and there. Again, as I said, it seems like the Modbus could be more versatile, but we are actually going to, and we know that PM bus is more standard for power supply industry. So we're going to collect feedback from make a final decision on and what Ethernet bus to use. As I said, the PMI, we may change the names because it's right now it's slightly confusing. We have a power management interface that works through Modbus, and we have another one called power management controller, which works through Ethernet with OpenBMC to allow fast data pooling. We may change the name actually to make it more intuitive to present the Modbus and Ethernet. So maybe on next presentation, on the next global summit, we come up with better names. On the high level, this is the approach with Modbus. The way that we are thinking about that is that the power supplies or BBUs directly communicate over RS-485. So the PMI module is essentially as empty board with some RJ45 connectors on the front. So what it does is pass through the PSU information, the communication through one bus to your top of rack switch. Same thing for the PSU. The benefit of this approach is that, compared to the V2, is that the power shelf and battery shelf are completely independent on communication, as opposed to the V2. You can daisy chain them again if you like, or you can directly connect it top of the rack switch. And if you want to have more power shelf or more battery shelf, you can easily do that. And so there is no problem there. I think the easiest number on the data speed that we can get with Modbus is 115 kilobit per second, which seems to be more than enough for most of the applications. The other approach with PMC at the high level is that the PSU, for either the PSUs or BBUs, they communicate with this module, PMC, the communication yet to be decided on the downstream. And there is a OpenBMC chip running inside the PMC that translates those PSU informations to Ethernet and send it to the top of the rack. There are more details to that. My team members, Zoe and Patrick, they are going to go through more details on the hardware and software of this one. Again, here the module, each power shelf and battery shelf, they have their own communication modules. So they are they work independently, and they are not relying on each other. So with that, I'm going to hand it over to Zoe to go more through of the PMC hardware design.
Thanks, Amin. So before we jump into the OpenRack v3 PMC, I wanted to give a quick summary of what we do in OpenRack v2. So OpenRack v2 design was about 5-6 years ago. We were going for simplicity. It was actually one of the first platforms where we enabled remote monitoring and firmware updates for our power supplies and anything power related inside the rack. So you can see on the application side, it was pretty simple things happening. It was essentially just sensor monitoring and firmware updates. On the hardware side, we relied on our top of rack switch to give us the outbound communication that we required. So at the shelf, we had power supplies talking to each other, and we were using Modbus RTU, and they were connected to our battery backup unit through SN bus, and they were essentially the bridge for getting information from the battery units. We made that connection to our top of rack through Modbus, and then our top of rack would be connected to our infrastructure network. Next slide, please. So if you, as you can imagine, this kind of structure, although it's simple, it's got limitations. One of the limitations was the implementation of Modbus RTU. Although we leverage a lot of existing libraries to enable Modbus on our top of rack, most of the APIs that we developed for collecting data, for data pipelines, any kind of actions or remediations were specific to us. Modbus itself is a limited protocol, and that's actually one of the reason its simplicity is an advantage. It is because it doesn't have too many features. What we were doing in our design run of V2 was using a shared bus. That meant that we had to do a round robin between all the connected devices. That meant going from power supply number 1 all the way to number 6 in one rack, and then going around again to get fresh data. As you may know, Modbus RTU is not a synchronous bus. There's no clock. So that does create some limitations when you try to do synchronous polling or when we have issues on the communication bus. We do have that top of rack redundancy dependency where we really rely on our wedge platform as top of rack because that enables us to run the Modbus APIs and the small piece of hardware that we require to run Modbus in our system. For firmware updates, we were at the mercy of the power supply vendors and the battery backup unit vendors because everybody does their own. One of the things that we're trying to standardize is the method in which the power supplies are updated. They can still be updated with respect to the power supply design, but from the infrastructure perspective, we're trying to standardize it. And you can imagine all these limitations lead to limitation in scalability. So next slide, please. For the PMC for OpenRack v3, the design is a little bit different. What we're trying to do is create an abstraction layer between our infrastructure and the devices that we're connecting to. And the intention there is through the abstraction layer, we can, what we're saying is we can connect anything we would like. This could be power supplies, it could be battery backup units, or it could be advanced cooling units that are being talked about for OpenRack v3. That makes the rack and the monitoring for our power system similar to how we do monitoring for servers today. With that, we would enable Ethernet, which is a physical layer standard that removes the limitation on top of rack switch, and it can give you an option to make a connection to top of rack switches, management switches, or directly to the infrastructure if that's something that's available. This hardware would utilize the existing PMC design that we use for servers. We'll talk about that a little bit more in details, and it would run OpenBMC. Next slide, please. So at high level, the block diagram would look like this, where we try to leverage PMBus to power supplies to the PMC. And we would be able to use SPS or Smart Battery System standard for battery monitoring. PMC would enable us to make a connection to the advanced cooling units or the liquid cooling units or whatever they may be in OpenRack v3 as well. We will try to enable some advanced monitoring features. We'll talk about that more in a few slides. We're trying to leverage a debug card because this essentially is a microserver. And we'll try to use the standard from our OCP debug card. Next slide, please. So this is a very high level block diagram of the PMC that we're exploring. The chipset here is not fixed. So right now we're using the ASP chipset, and that's something that works for us. The reason is that it's something we're familiar with. We're using it for our server monitoring and a bunch of other devices. So we're kind of building on top of that. But it's not necessarily this chipset that can be used. It could be other chipsets. So most of the blocks that you see here are for the functionality of the ASP chipset and the connections that I talked about between the power supplies or other devices that you may be connected to. Next slide, please. What this means is that with the abstraction layer, we can have direct connection to every device that we're monitoring. That would mean that we can maximize that communication between devices and store all the information in memory space, and then collect all that in a different memory buffer inside the PMC, and then from the infrastructure network, we would access that main buffer. That way, we will not have any round-robin approach. We will have direct communication to every device. And this can happen autonomously, where we can, while we're maximizing device-to-device communication, we're not dependent on the network, infrastructure network either. So if there is a bottleneck on the network side, then we'll have the information that we require stored on the PMC and we can collect them later. There's also a daisy chain approach here. I'm showing up to n number of devices. There's obviously going to be some hardware limitations there, but this kind of daisy chains allows us to connect more than one PMC together, and we can treat one of them as the outgoing port to the infrastructure. So you could have multiple shelves, multiple power shelves, multiple battery backup shelves, or other devices connected through the PMC to the network. Next slide, please. I won't spend too much time on the advanced monitoring slide here, but the point here is that 6-7 years ago, when we started doing monitoring for OpenRAC v2, like I mentioned, we were going for simplicity. We didn't have too much flexibility in our infrastructure to turn things on like waveform capture or event logging at outside of just device level. That's something that we want to pursue. Our infrastructure is evolved now, and we have the tooling in place to be able to turn on features like that. As well, with the chipset on the PMC, then we can do maybe more computationally intensive algorithms on the device itself. For example, more advanced state of health or state of capacity calculations for battery backup units. Next slide, please. So as you've seen, the theme here is to use a lot of already existing standards. So SMI is one of the big ones. And the interesting thing there is that it not only gives us the capability to communicate to power supplies through a industry standard bus structure, it also gives us the capability to connect to our battery shelf through the SPS standard. And we'll also be running OpenBMC, as I mentioned, Redfish, and OCP debug card. And with that, I'll hand it over to Patrick, which he'll be talking about those in detail.
Thank you. So like Zoe said and Hamid said, in this design, we're looking to really leverage a lot of existing open standards and open source software. Because this device is in a lot of ways similar to management that you might do on a top of rack switch or a compute server, there's already an existing open source project that Facebook's involved with and many other open compute companies are involved with called OpenBMC. So OpenBMC is a software stack that's loaded onto the server to perform out-of-band management of a server. BMC stands for Baseboard Management Controller. So like I said, we already support this on our compute systems and top of rack switches. And the project as a whole has about 35 member companies that participate in the project on a regular basis. So it's yeah, Hamid, you can go to the next slide. Right, so looking at the PMC, because we're picking up an existing open source solution for management, there is a lot of capability that the software stack has built into it. An example of that would be sensor monitoring for like temperature sensors and those kind of things. But because this problem domain is different from what OpenBMC currently supports, there are some device-specific features that we're needing to enhance to it. So an example would be firmware update. The OpenBMC software stack has standard interfaces for doing software update, and you can access those software update interfaces over various management interfaces such as Redfish or SSH. What we'd be doing is extending that same firmware update interface to be able to update the PMC itself, update power supplies, update the batteries, and eventually potentially the cooling units. So it would use the exact same interfaces that OpenBMC uses today for software update, but instead of giving a BMC image or a BIOS image, it would be extended where you can give it a power supply firmware image, and the PMC will then do the work to go update that power supply for you. I mentioned sensors, metrics, and telemetry. And this ties into what Zoe was just talking about as well with some of the high resolution data capture. So OpenBMC has interfaces for getting metrics and sensors from a server or from a top of rack switch. And we'd be extending that for a lot of the power domain specific sensors. So an example would be maybe like the battery, the current charge values of the battery, we'd be able to extend the sensor subsystem to be able to give that information out. And also power supplies and batteries have kind of unique device error reporting that isn't supported. And also a feature that we're looking at within our data center is being able to configure the battery charge rate. So when the battery, for instance, when there's a power outage, you don't want all of the racks in the whole data center to be pulling power, trying to charge their battery at a max rate. So we may use some configuration to, at a data center level, level out the battery charging. In the slides here, we've got a link to the tentative feature list of what the PMC will be implementing for all the features if you're interested in that. Next. I talked a little bit about management interfaces. So the three that we're planning on supporting on this device is SSH. OpenBMC supports that already, so you can SSH into a BMC device, and there's a command line interface for doing systems management and many of the operations you might want to do. Redfish is another management interface that's also supported by OpenBMC. It's a standard that's created by DMTF for doing device management, server management, system management. So it's a REST API, if you're familiar with that, using similar technology to what web browsers use to interact with the server and collect all of the management data from the device. And then the third one, which OpenBMC supports and may be interesting in some environments and maybe not in others, is a web user interface. So we can very easily, because we're using this open source stack, using Redfish, we can enable a web interface, web UI, to manage the PowerShelf, the PowerShelves themselves. So we have a little picture here of what the firmware update screen might look like. This is actually taken from a OpenBMC server that we have today. Next. Right, so firmware update, I've talked about this a little bit. We're going to extend the firmware, the PMC, to be able to support firmware update of the power supplies, the battery shelves, and itself. And the two mechanisms that you do that within OpenBMC today are over SSH or over Redfish. So with SSH, what you can do is you can copy an image over SSH to the PMC or to the BMC. And once you copy the image over SSH, the BMC will automatically recognize that you've copied an image to it, and it will, in the case of like a power supply, it will identify that that image is for a power supply. And then there's a command that you can run to activate the image, it's called, which will be what tells the PMC to go over PM bus, for instance, or over Modbus and update the firmware of the power supply. Similarly, in Redfish, there's a standard API for doing that. It's called update service. So again, update service handles generic software updating, and then what we'd be doing is implementing the specifics of power supplies and batteries within the PMC. And so, like Zoe went over in the hardware, the interface to the batteries and to the power supplies is standard interfaces, PM bus and SBS. So the ability to do those updates would be using those standard interfaces, and then the PMC would be providing that software abstraction to use standard protocols like Redfish to do that update. Next. Great, so call to action and summary. We've got a link here for the draft specs for the device. We'd really encourage anybody that's interested, either end customer, suppliers, other OCP participants, to reach out to us and give us ideas and suggestions. Like we said, we're building this on open source software, and so we'll be actually doing the development in a public way. So as we're developing the software, you'll be able to see that show up on GitHub within the OpenBMC project. So you're also, if you're interested at a software level, able to reach out to us there. There's a number of other related presentations that are going on later today about ORV3, so watch out for those and join if your interest is. I think that's all.
All right, thank you. Caleb, do we have time for questions?
If we could squeeze one in real quick, only about 60 seconds. There was a comment that was published. Redfish has published support for PDUs, and they're working on extensions but they would like more subject matter experts and feedback to get it right. So that was just one comment.
Okay.
Good, good.